Now we'll turn to comparing the results between regular LTA and RI-LTA. We'll also talk about how one decides on the number of classes and further on checking model fit and model modifications. On slide 40, you see then a simple tabulation for regular LTA and RI-LTA, number of parameters, log likelihood, and BIC. And we see that RI-LTA has 5 more parameters than regular LTA. That corresponds to the 5 factor loadings for the random intercept factor that we hold equal across time. So 1 for each of the 5 latent class indicators. And you notice then what a big improvement we get in the log likelihood. Minus 20,000 is far higher than minus 21,000. It's about 1,500 points better. And in terms of BIC, it's also a big improvement. BIC being lower means it's better. That is, weighing the likelihood together with the number of parameters to get a BIC value. It's easy to get a better likelihood by just increasing the number of parameters. So we have a penalty in the BIC computations, which prevents you from simply increasing the number of parameters. The log likelihood ratio chi-square difference testing that we typically do, 2 times the likelihood difference is chi-square distributed with the difference in number of parameters. That's not quite right here because the two models differ with respect to a factor. So a random effect, so you have a variance of a factor involved here. So saying that that factor doesn't exist, which we say for regular LTA, means that we are testing on the border of the parameter space, which renders the chi-square distribution assumptions invalid. So it's not exactly chi-square distributed. It's probably not far from it, and actually would be interesting to do a Monte Carlo simulation study to see how close or how far away it is from a chi-square distribution. Now, I would say that it's not needed to get into chi-square difference testing because we have such large differences in the log likelihood and in the BIC. And in fact, we can stay with BIC as the only gauge of model quality, relative model quality. It's clear that this value is so much better than the value up here, and sometimes though we want to keep track of the log likelihood to see if it improves or not. That also relates to model identification issues. Now BIC is good because it can be used even for non-nested models or for models that are nested but still have this problem of testing on the border of the parameter space, the zero variance issue, as long as you have the same dependent variables. And that's the case here. You have the same 20 binary latent class indicators. So let's take a look at the estimates then from the two models and see how they differ. So first we start with the measurement probabilities for the 3 classes, regular LTA and RI-LTA. And we have the 5 binary latent class indicators here. And we remember this pattern from segment 2, going through the example. We find that the beginning item is indicative of being in at least class 2. It's not a high probability in class 1. Similarly, ending is indicative of having reached class 2. And site is indicative of having reached class 3 proficiency. On the right, you see a fairly similar pattern. That is, we get a strong increase in the probability going from class 1 to class 2 for the beginning item. Not as clean as over here. There's a probability 0.3 here, whereas 0.07 here. And for the ending item, there you have more similarity, although you have a little bit higher probability for class 1 here. So less discrimination. Same thing for the site item. Similar pattern, but a little higher probability of being class 2. So less discrimination between class 2 and class 3 in RI-LTA than for regular LTA. And that may be a pattern that we will see more often. It is actually a function of how we specify the model with a random intercept factor. I described that in the psychological methods paper when I talk about the measurement model. However, you can see it as a more correct representation of the discriminatory power of the items because the RI-LTA model fits the data so much better, as we saw. Slide 42 then talks about the latent class probabilities at the different time points. So each of the 4 time points here, and here are the 3 classes, and we have regular LTA at the top and RI-LTA at the bottom. So starting in the fall of kindergarten, regular LTA says that we have about 69% in the lowest class, whereas RI-LTA says that we have about 95% in the 0 class. So quite a big difference here. And you may ask then, well, which one is correct? Well, RI-LTA fits better, so that would tend to make us believe that this number is more reliable. But we'll take a closer look at the fall time point and see if that holds up, that RI-LTA fits better in that part of the model. Likewise, if you go to the end, regular LTA says that 81% have reached the highest proficiency class 3 at the end of first grade in the spring. Whereas RI-LTA says it's 97%, so quite a bit higher there as well. So there are clear differences here in the interpretation of the data. And one can argue that regular LTA, if it fits much worse, shouldn't be trusted. Slide 43. Here we take a look at the key issue of transition probabilities. You have at the top here you have regular LTA, and at the bottom RI-LTA. On the top left you have the transition from the first to the second time point, fall of kindergarten to spring of kindergarten, and on the right you have the transition from fall of first grade to spring of first grade. So I'm showing you 2 of the 3 transitions. What I left out is the transition from spring kindergarten to fall first grade. So regular LTA says that for those who start in the lowest class in fall of kindergarten, 34%, there's a 34% chance of staying in that low class versus a 65% chance of moving on, which would be a better outcome. If you go down to RI-LTA, it says that you have a much lower chance of staying in class 1 if you start there, and a higher chance of moving on to class 2. So those who start in lowest class of fall kindergarten have an 82% chance of moving on to class 2, which is quite a lot more optimistic of a result than for regular LTA. You can also look at the transition from fall first to spring first, and for instance you could take a look at, for those who were in class 2 in the beginning of first grade, probability of staying is 13%, of moving on to class 3 is 86%, whereas again RI-LTA has a more positive view, smaller chance of staying in the same middle class, and a higher chance of moving on to the better third class. So different interpretations. Going to slide 44, we get back to the issue of typical transition paths that I talked about in segment 2 for going through the example before we got into all the methodologies. So here are the estimated frequencies for the 3 most frequent paths through the latent class variables over the 4 time points. So this row is then the most frequent path. 33% of the individuals follow that path. That is the path of starting in the lowest class in the fall of kindergarten, going on to the higher class 2 spring, staying there over the summer, and then going to class 3. 33% follow that path. Whereas for RI-LTA, you have 71% following that path. And going to the more beneficial path, starting already in class 2 and going to class 3 already in spring of kindergarten and staying there, that was 10% for regular LTA, whereas we don't even have that path among the 3 most likely, so it's less than 5%. So clear differences. And again, just to remind you that this kind of information is shown in Tech 15 under the heading Final Class Counts and the proportions for the latent classes based on the estimated model. Turning to slide 45, we should discuss the key issue of deciding of the number of classes. We're going to use BIC here, and we're going to talk about 2 approaches: 1 time point at a time, or analyzing all time points jointly. And this is, again, we're talking about analysis without covariates. So here you have the number of classes, 2 to 5. And commonly for regular LTA, you start with an LCA, a latent class analysis, for each of the 4 time points. And here this is shown, the BIC values are shown for 2, 3, and 4 classes. And you see that the bolded value here is the lowest, that is the best for all 4 time points. That is, this would indicate work with 3 classes, which is also substantively motivated, as we have discussed the 3 stages of reading proficiency acquirement. Now you can also analyze all time points jointly and vary the number of classes. And you see then that BIC keeps going down, and it does not show a minimum like it did here, where it dipped down and then went back up. In every case, it dipped down and went back up. That's what you want to see to be safely guided by BIC. Here, that doesn't happen. And that could be an indication that you are not hitting on the exactly correct model. Some modification of the model may be needed for this minimum of BIC to show up. If you continue with 6 here, you might see, yes, another drop in BIC. And I think I found that, and not an increase. So no minimum seen. RI-LTA, all time points jointly, says the same thing. That is, you don't find a minimum, so there too there may be room for improving the model. Now, for RI-LTA, I didn't show the separate time point LCAs because, unlike regular LTA, a model for 1 time point at a time is not a subset of the RI-LTA model. For instance, if you do a latent class analysis plus 1 factor, like a factor mixture model, that's not a subset of the full model because it doesn't capture the time invariance of the factor loadings. So it's really a different model. So with RI-LTA, you would have to go with joint time point decisions. And we will see what the reason might be for this lack of a clear BIC decision on the number of classes. And this last bullet we already covered. See Tech 10 for model modifications or model misfit, then try a more flexible or an alternative model.